Hello and welcome everybody to this mini course on disordered quantum systems. So first I want to give some overview and mention some results. And then I want to give you also some mathematical aspects and showing you with which kind of methods one can obtain some of these results. Okay, so so let me just start quickly with mentioning quantum systems. I'm pretty sure all of you know. So if you have a quantum system, then the motion of the electrons or the particles is typically described by a so-called Hamiltonian. Okay, that's a superjoint operator in a separable Hilbert space, and typically we use the L2 space over some countable graph in the discrete setting, or we use the space of L2 integrable functions on RD. And sometimes we take tensor products of these spaces with some finite vector space CR, a finite dimensional vector space CR. If we have what's called internal degrees of freedom, or in physics also sometimes called spins. Okay. The vertices of the graph G for discrete models, or the space RD in the continuous models, are the possible positions for the electron or the quantum particle, right? And well, if we have CD or RD, then we have a quantum system in D dimensions. Okay. For discrete models, one can actually think of the vertices of the graph as the positions of the atoms, and the electrons kind of hop from atom to atom. So these are sometimes also called tight binding models. Well, if we have a vector in our Hilbert space of norm 1, right, then this is associated as a pure state of the electron. And if we take some lattice site x and look at the value psi of x absolute value squared, then that's the probability to find the particle at this position. And in the continuous case, okay, this is the probability density to find the particle at that position. And the free motion of the particles is typically described by a minus the Laplace operator, okay, in RD. And well, in the discrete case, there is some discrete Laplacian, or very often we use the adjacency operator, or minus the adjacency operator of the graph. And if we have an electric field present, then this will be described by a potential operator. So that's some multiplication operator of this sort. So this is called potential. And a Schrödinger operator on L2 of G or L2 of RD is then the sum of these two types, right, of minus the Laplacian plus the potential. Okay, so these are the quantum systems we will look at. And so why disordered quantum systems? So well, if you have, for instance, doped semiconductors, right, then the doping is a random process. And you have relocations of the excess electrons if you have N doping. So if you introduce some atoms that have some electrons more in the valence band, or if you introduce some that have less, then you have so-called holes. And okay, so when you do this, then the valence electrons will relocate them a little bit in the whole solid, and this will create a random electric field, okay? And this random electric field creates a random potential for an electron that you inject into the material. So when you look at electrical conduction, right, for instance, and then it travels through the solid, and then, okay, so you will experience a random potential. And so you model this by random Schrödinger operators, where you have a random potential. Okay, and then sometimes you do some perturbative analysis, and you will add a coupling constant, and that's often called lambda. Okay, and so you have this operator family H lambda omega, which is minus Laplacian plus lambda times a random potential V omega. And okay, so omega notes the element in the probability space on which these operators will depend. And okay, you may also add some periodic potential sometimes Okay, because maybe you have some material that has some periodicity. Okay, and then you add some disorder to it. So this part, this random part, lambda times the omega, is what describes the disorder of the material. And if lambda is very big, much larger than 1, so okay, so then this means large disorder. And if lambda is well still positive but much smaller than 1, then this means small disorder. And okay, so this may feel a little bit contradictory, right? So something between 0 and 1, how can it be much smaller than 1? So this is in sense of scales, right? So it might be better to think of logarithm of lambda as very big, and here logarithm of lambda is very negative and big in that sense. Okay, well, so the most prominent example of this type of models is the Anderson model, named after Anderson, who kind of started with this paper on this kind of theory. So if we have, for the discrete Anderson model, we will have a graph G, and we look at the space L2 of G, right? And then we look at the operator where we take, okay, so here minus the sum of nearest neighbors of x psi of y, plus, okay, and here's the multiplication operator, with the potential at site x, which is equal to lambda times omega x. And okay, so d here is the graph distance, and the graph distance means, okay, so the graph distance is 1, means it's the nearest neighbor. So graph distance is the number of edges you need to get from one side of the graph to another vertex of the graph, right? And if you take, for instance, let me do an example here, the space L2 of C, right? So in that case, Laplace psi of x is you take the sum over the neighbors. Now for x, you have just 2 neighbors, right? X plus 1 and x minus 1. So in this case, you have that adjacency operator. Okay, so that's the kinetic term. And well, if you take C2, for instance, right? Then the graph structure we associate with C2 is kind of this type of edges parallel to the axis, right? And then so every point has 4 neighbors, right? And so here you have a sum over the 4 neighbors. Sides. Okay. Now these random potentials, these are supposed to be independent, identically distributed random variables, right? This omega x for x in G. And the typical normalization is that the expectation is 0 and the variance is 1. So in particular, we very often want to assume that it actually has a variance. Okay, and sometimes one needs stronger assumptions, like the distribution being absolutely continuous with respect to the Lebesgue measure or compactly supported. Yeah, and okay, in the classical d-dimensional Anderson model, we have the graph CD, and the graph distance in CD is the 1 norm, right? So the number of edges you need in order to travel like from one to another one is the 1 norm. Okay, and well, you can have some variant with matrix potentials. So you take the tensor product with CR, right? And then, okay, this omega x, this psi of x is vector valued, and then this one here has to be matrix valued. Yeah, some symmetric R by R matrix. And then you can add some term I psi of x, which you can, in some sense, think of a vertical, a Laplacian or vertical operator in a slice, because so if you have a product graph, so for instance, take this finite graph and take the product with C, right? Then when you take the product, you get a strip. Okay, and then the A psi of X is kind of living here in the slices, right? And can be seen as the Laplacian in this vertical direction. And then so what you get here is kind of operators on strips, right? Of course, they also fit this framework if you just instead of the graph G, think of an operator on the space of the product graph. Okay. Well, for continuous Anderson models, you don't have like these lattice sites, right, to make a random potential there. But what you can do is you first define a potential bump function, and then you relocate this bump onto the lattice sites, CD, and the amplitude will be random. So you define some u of x, which in one dimension, for instance, might be some shape of this type, possibly compactly supported, but okay, not necessary. Very often assumed kind of okay, strong enough decay here for these pump functions. Okay, and think of this as a potential bump function centered at 0, and then you look at u of x minus n as a potential, right? So then this is centered where n is in CD, so this is centered at the lattice point EVD. So if x is n, then you have here u of 0, right? You have here the center. And you multiply this potential pump by some random variable omega n, and this omega n's is a family of IID real valued random variables. Okay, and you may add some periodic potential, and then you have a continuous Anderson model. This is how I want to call this. And okay, so this part here is the nice part with the periodic potential, maybe describing some metal, some nice periodic crystal structure, and then you get here the disorder. Okay, and there are some variants to these models that instead of CD, for instance, you can center the random potentials, the bump functions here at some Delaunay set, and the Delaunay set is okay. So think of it maybe as an aperiodic lattice or something. Okay. So I won't be more precise here. Okay, so these are the type of models we look at, and the Anderson models, they have some very nice property. Well, the Anderson model in CD and this continuous Anderson model, they are what's called ergodic operators. So to model our random operators, strictly speaking, right, we need to introduce a probability space, okay? And then our operator in that sense will be some kind of measurable, weakly measurable function from omega into the set of self-adjoint operators. Okay, and well, to get ergodicity, okay, so we consider some group of measure preserving transformations on the set omega, and we want the probability measure P to be ergodic with respect to this group. So that means sets that are left invariant by all these by the whole group of the measure preserving transformations, these sets have probability 0 or 1. Okay, and so now for an ergodic operator family, what we need is a representation of this group of measure preserving transformations on the Hilbert space H by unitary operators, such that we have this what's sometimes called covariance relation. So we take the random operator H, okay, that associated to T omega for this transformation, and this is a conjugation, unitary conjugation of H omega. Okay, then we say that H omega is an ergodic operator family. And okay, so how does this work in these examples? So this looks kind of maybe a bit abstract, but the typical situation is the following. So we have IID, the variables, so the measure preserving transformations are permutations of these ones, right? And in particular, we use permutations that come from graph automorphisms of G. And then the unitary operator is the corresponding unitary permutation matrix, right? And then you get this relation, you get it automatically for the potential, because, right? And if you have a graph automorphism, then you also have this type of relation for the Laplacian, so you get it for the whole random operator. So, so if you think of CD, right, what happens? So C2, for instance, one of these measure preserving transformations that's a graph automorphism is, for instance, just shifting, right? If you shift the lattice up, you get the same lattice, okay? So, and then, so this shift clearly is a unitary, okay, it translates into a unitary operator on L2CD. And the Laplacian is invariant under this, the discrete Laplacian under this unitary operator, because, well, it's a graph automorphism that you have. And you can also use the group of CD translates on RD. So especially in the CD case, this group T, right, is also isomorphic to CD, right? It's just, it translates on CD, so given by CD, basically. Okay, and well, you can also show that you have this type of ergodicity for the beta lattice, for instance. Okay. Well, now, and ergodic families will have kind of some nice properties that I will mention in a bit. Before that, let me generally introduce what are the objects of interest that we study. So, of course, well, the main important thing is the spectrum and the spectral types. So, as you probably all know, if you have a self-adjoint operator, okay, then the Hilbert space splits into a pure point, an absolutely continuous, and a singular continuous part. Right? And then you can restrict your operator H to these subspaces, okay, and look at the spectrum of these restricted subspaces. And so this way you define the pure point spectrum, the absolutely continuous spectrum, and the singular continuous spectrum in the sense of closed sets for the operator H. And the central question is, what are these sets for these random operators? And okay, so one of the most important things in the ergodic case is if you have an ergodic family, then the pure point spectrum, the singular continuous spectrum, and the absolutely continuous spectrum are almost surely non-random. So this means there are fixed closed sets, sigma pp, sigma sc, and sigma ac, such that the pure point spectrum is almost surely that, the sc spectrum is almost surely that, and the ac spectrum is almost surely this set. And now something that I should mention here, so the pure point spectrum is induced by the eigenvalues, right? But this does not mean that the eigenvalues are almost surely the same. This is as a set of the pure point spectrum. So this set is the closure of the set of eigenvalues. So what happens in this random case is when you have pure point spectrum, typically is that you have dense pure point spectrum in this set, sigma pp. So the closure is this set, right? But the eigenvalues actually are highly random. So typically the probability of a fixed value E to be an eigenvalue is 0, right? So, okay, so the eigenvalues move, but they always form a dense set within this. Okay. Yeah, another object of interest that one wants to study is the so-called density of states measure, or integrated density of states. So, okay, so what you do is basically, well, you have your model in like the whole space, RD, or in your whole graph. So let me think of RD and CD now in particular, and then you restrict your model to a box, right? A box lambda. Okay. And you look at the restriction H lambda to this box, and in the continuous case, we assume some kind of Dirichlet boundary conditions here. Okay, and then you look at the density of states measure in lambda for each of your operators. So what you do is, I actually see there is some small mistake. You don't really need this here. So so yeah, so the way to do this is somehow okay, to look at this trace of the function of some function f of h lambda, and you normalize it by 1 over the size of lambda, where this is, okay, in the continuous case the Lebesgue measure, and in the discrete case, okay, the number of elements in this subgraph. And yeah, I'm sorry. So if you use h lambda, you actually only need to take the trace of f of h lambda. If you take here the full operator h, then you multiply by this indicator function 1 lambda that you can do. And okay, so in the discrete case, let me look at this a little bit more closely. So when you look at this trace, right, then this protector 1 lambda, okay, so you can write it like this, like a sum of rank 1 projections onto the sides in lambda, okay, and then this trace is the same as just taking this sum here. So what you do really is you average over your box lambda all the spectral measure at all the lattice sites x, okay, and then what you expect is somehow, so at least in CD, for instance, by ergodicity, is that this actually converges to the expectation of the spectral measure, okay, at the site x, okay, and this is by okay, by this invariance of shifts, this will be the same for all x. This is the density of states measure at the end if you go with lambda towards CD. So the density of states measure in general is when you have these random measures, okay, defined on these boxes lambda, and you take the limit of lambda going to the whole graph G, or in the continuous case towards RD. If this exists, then this limit is the density of states measure. Okay, and the integrated density of states is then just the density of states measure applied to the interval from -infinity to some NHAE as a function of E. Okay, and well, as I already kind of indicated here, one of the points is that for ergodic operators, the density of states measure, or the integrated density of states, exists almost purely in the non-random objects. Okay, so this is one of the things one studies. Another aspect one wants to study with these type of operators is the so-called level statistics. So again, one restricts the operator to big boxes lambda, okay? And then one looks basically at the eigenvalue process. So because we have these Schrödinger operators, when we take compact boxes in RD, or well, finite subgraphs in the discrete case, then the spectrum of this H lambda of this restriction will be given by eigenvalues, right? And so you can look at these eigenvalues, okay, so how close are they to some fixed energy E? So you look at the spectrum of H minus E. And then these are random points, and you think of it as a random point process, and then you kind of rescale it with some m lambda when the box gets bigger, because, okay, so the bigger the box, the more eigenvalues you have in some sense, and the denser they are, so that the average spacing gets smaller and smaller. So then you rescale them, that you have an average gap size of 1 for the two eigenvalues closest to E, for instance. Okay, and then you have this type of point process, okay, of discrete points, and you look if this has weak limits when you converge with your box to the whole graph G or to the whole RD. Okay, and these point processes are also of interest because they tell you something about more closely in a small regime on how eigenvalues look. So the density of states kind of tells you a little bit on overall the shape on how much eigenvalues you have in a region, and then this thing here, the limiting point process, tells you for large boxes how close to each other eigenvalues can get, if there is some level repulsion, or okay, if they are essentially kind of independent and there's no repulsion at all. Well, okay, and the last object of interest I want to introduce is about the dynamical behavior. So, okay, so we start with some vector in the Hilbert space of compact support, so with some state that is localized in some compact region, or in discrete case finite region. Then we look at the projection onto energies in some interval E, right? So this is like this indicator function of the operator H, then applied to psi. And then we look at the evolution of this one and the peak moment of its distance from some origin. Okay, so in a graph, if it's not CD, then we just assign some origin, some random lattice point 0. So this means, okay, we look at the evolution, so e to the minus ith of this projection 1ih of psi, and its value at x, which I've written here in this kind of fancy way using Dirac notation, right? So this is a two vector localized at x, and then the scalar product x psi, okay, then it's scalar product of these two, and that's basically a fancy way of writing psi of x. Okay, and then we take the absolute value squared of this and we multiply by the distance from 0 to x to the power p and sum over all lattice points in the lattice case. And then, well, if we think of this as a multiplication operator, okay, multiplying the state x with this value, V0x as a multiplication operator, absolute value of x, then this thing here is actually the same. So you say this product here is just the value of this vector at x. So then you can see that this one is actually the same as this norm here, right? So you take here the evolution and you multiply this with this multiplication operator and distance operator, absolute value of x to the p over 2, and then the whole norm squared. And this is actually how we define it in the continuous case, right? Okay, so this is this p-th moment of the distance after time t. And okay, and well, this is the probability to find the particle at site x after time t, right? So it tells you a little bit about the moment of how fast of how far the particle has traveled at a time t in average. And so, well, if it basically doesn't travel much, so over all times t. So if the supremum over all times t of this quantity is bounded by some bound that may depend on the initial state psi, then we have strict dynamic localization. Okay, and well, if we have diffusive motion, then we expect that with time t, we travel a distance of square root of t. And so then this p moment grows like t to the p over 2. And for ballistic motion, okay, we expect a fixed velocity. So the distance traveled is approximately proportional to t. So we expect that this p moment grows like t to the p. Okay, well, there are some connections between the spectral picture and the dynamical picture, but okay, so in general, these connections is kind of it's kind of a weak one. So it doesn't tell you that much about the dynamics if you know about the spectral type, but okay, it tells you something. So if you have, let's go to the discrete case. If you have a sequence of boxes like this that grow towards the whole graph, okay, and we let PL denote the projection onto the space of functions supported in this box, then we have this characterization of the continuous Hilbert space and the pure point Hilbert space. So this is the vectors they have pure point measure. This is the vectors they have continuous measure. Okay, so in the continuous case, you look at the evolution and then you project onto this box B, and then you take this norm squared, which is the probability to find your particle in the box of size L after time t. And you average this probability over times from 0 to capital T and take dt to the limit. And then you take the box size limit to infinity, and you get that this is 0. Okay, so this means that for large L, okay, so this all of this will be eventually small. So you're not travel. So you're kind of okay. So you're traveling outside the box for larger and larger L. If also T gets large, you will travel outside the box of any size. So this means your particle somehow will travel towards infinity. Whereas in the pure point start, if you project onto the part that's outside the box, so 1 minus PL, right? Then this part, you take the supremum over all times, and the limit in this part is 0. So which means for very, very large boxes, there's only a small part outside that box, and this is for all times t. Okay, so your particle stays basically in bounded regions. Right, so this is the interpretation. Particles with states in the continuous spectrum travel, and particles with states in the pure point spectrum have over all times only a small probability to be outside a large finite box. Okay, but it won't really tell you here much about, okay, whether you have diffusive, ballistic behavior, and things like that. But okay, so for these random models, we actually have some very precise expectations. So so for these random models, one should see maybe non-metallic phases and also metallic phases. So the non-metallic phase, we have what's called Anderson localization. So this is a dynamic localization, pure point spectrum, exponentially localized eigenfunctions. And because of this, eigenstates that are localized in different spatial regions where potentials are independent, will lead more or less to independent eigenvalues, right? In these kind of big boxes. So you have one and then one other one where you have the different eigenfunctions, one that's more centered here, another one more centered there. And then the eigenvalues will be independent. And if you drop independent eigenvalues into some interval and you rescale them, then the limiting process will be Poisson. So this is like you get the Poisson point process for the level statistics. And In the metallic phase, okay, you have delocalization, so diffusive behavior. You think of you expect absolutely continuous spectrum. Eigenstates are spread out. Well, eigenstates are not really kind of not L2 normalizable, right? In this case, they're not really eigenstates in the L2 sense. And this should lead to level repulsion, and the universality conjecture states that you should get something, some process similar to the Gaussian orthogonal ensemble. Okay. Well, so these are kind of the heuristics. And okay, heuristics from physics is that localization is expected in low dimension and at large disorder, for the discrete models especially, and delocalization and Anderson transitions are expected to exist from some dimension on. So Anderson transition means that, okay, you have metallic and non-metallic phases, and there's, depending on parameters, energy, and the disorder, you have some transition. Okay. Now, the conjectured delocalization and absolutely continuous spectrum for a d-dimensional continuous or discrete Anderson model, d greater or equal than 3, is still an open problem. And the conjectured localization for the discrete two-dimensional Anderson model, that small disorder, is also an open problem. Okay. Well, so let's look at some of the results that we get where the localization actually is proved. So in discrete models, the Anderson localization is proved at large disorder and for sufficiently nice distributions of the potential for any graph with finite connectivity, including CD, beta lattice, and okay, some more general things. And there's some general method by, I'm sorry for this typo, Eisenman-Molchanov. And okay, so it's called the fractional moment method. And I'm mentioning Tautenan here because there's a paper where he basically looks at what's the most general type of graph where this still works. Okay. Now, the most singular type of potential one can think of is the Bernoulli-Anderson model, where one has basically only two different values for the potential. Yeah, so like for instance, probability 1/2 is equal to 1, probability minus 1/2 is equal to 1/2 is equal to -1. Sorry. Okay, and for the Bernoulli-Anderson model and large disorder, localization is proved with very recent works in C2 and C3. In 3 dimensions by Li and Li Chan. At the edges of the spectrum in any disorder, you find it, okay, also the Anderson localization. And well, in quasi one-dimensional models, so on C and product graphs, yeah, strips, basically, you also find localization. Okay. For continuous models, okay, what is known? Well, the Anderson localization has been proved basically at the bottom of the spectrum in any dimension D. So you have some interval. Typically, you have the models like this that you have an infimum energy in the spectrum, okay, and so in some interval like this, you find Anderson localization, including for singular distributions of the potential, like Bernoulli distribution, which is a work by Borgan and Koenig. Okay, and if you ask for large disorder localization, so what you can do is, so if you add this coupling constant lambda, you can verify for certain models, if you choose your distribution right, that okay, this increment energy is some constant, maybe 0, the independent of your disorder size lambda. And then if you take some fixed energy E and you take lambda sufficiently large, then you may find that this E0 is bigger than E, meaning that this E will be inside this interval. Okay, so fixing an energy E and getting disorder large enough, eventually you will find that you have localization there, and in this sense you have also some large disorder localization results. And well, in dimension d equals 1, including singular potentials like Bernoulli, and okay, so the most general work here is by Damanik, Sims, and Stolz. Okay, now there are also some extensions to Anderson-like continuous models, for instance, in aperiodic media, so potential centered at Delaunay sets. And there's some work, for instance, by Kaimene, Müller, Irojas, Molina. Okay. And then let me talk about delocalization results. So the three-dimensional, the CD models, and also the RD models somehow are still out of reach, right? But people have looked at maybe other graphs that have some advantages for proving delocalization. And so the first result to get existence of absolutely continuous spectrum for the Anderson model is on the beta lattice due to Klein. And okay, there's some very interesting work by Eisenman and Warzel that actually you have quite a big region where you have AC spectrum bigger than expected before. And okay, also product graphs of the beta lattice with finite graphs, which we call beta strips. Okay, so this is the, this is the beta lattice. So it's a regular tree, right? So here every vertex has 3 neighbors, for instance. Okay, and then if you have a beta strip, then you make the product graph of this beta lattice with some finite graph. So here's a beta strip of width 2, for instance. Then one can extend this to trees of finite cone type and tree strips of finite cone type. Okay, so there's trees where you have different types of vertices, and and you have some kind of rule that so here we have 2 types of vertices, and every vertex of this type has 2 children of this type and 1 of that type, and every vertex of that type has 2 children of this type and 2 children of that type. So you don't get a regular tree, but okay, something structured like this. And then it has also been shown on anti-trees of d-dimensional growth rate for d bigger than 2. In case where the distribution is also kind of compactly supported. Okay, and an anti-tree is, okay, so it's called anti-tree because you kind of have locally complete graph structure. So you have here kind of your shells, and between neighboring shells, you take all possible connections. Okay, so this is how it looks like. And then for the Anderson model, actually one has to make some small twist. One has to, because its number of edges grow very, very rapidly, one has to renormalize the edge weights. So you have to change the Laplace operator a little bit. Okay. Okay. Well, so this concludes the first part, giving some overview. And okay, so in the second part, I want to get a little bit more detailed into some mathematical aspects, and want to start with localization and the fractional moment method.